Hello everyone, my name is Yearning, and welcome to part 4 of C++ Tetris. Today we are going to deal with the Tetrominoes. This video ended up being so long that I had to split it into two parts. In this first part we are going to get familiar with the Tetromino shapes, then we'll design a good way of representing them in memory, and finally we'll try to display them on the board. So, the classic Tetris game has 7 Tetrominoes. Each one of them has a different name, color, and shape. We have the straight, square, T, J, L, skew S, and skew Z. I am aware that the original names are only one letter each, but we would like to avoid the one-letter names in our code, so we'll stick to the larger ones. We need to figure out a way of representing and manipulating these shapes on our board. First of all, how do we store a Tetromino in memory? How do we represent the shape itself? If we analyze the shapes, they are obviously in 2 dimensions, so it's probably safe to assume that we are going to represent them in a 2-dimensional array. A matrix if you want. For the straight shape, it's a simple 4x1 matrix. For the square, we can store it in a 2x2 matrix. For the T-shape, it's a 2x3 matrix, and so on. But it's actually not enough. Don't forget that the Tetrominoes need to be rotated. Let's take the J shape as an example. It requires a 2x3 matrix. If I rotate it, it doesn't fit anymore. Suddenly, we need a 3x2 matrix to store the shape. If I rotate again, we go back to needing a 2x3 matrix. And so on. So as you can see, having to change the size of the matrix every time we rotate is quite inconvenient. We need another solution. Some of you may have already figured it out, but let's take the straight shape as an example. We need 4 columns to be able to store it like this, but as soon as we rotate it, it now requires 4 rows. What was a column requirement now became a row requirement. In a similar fashion, if we rotate again, the row requirement becomes a column requirement, and vice versa. So, with this observation, we can deduce that the biggest requirement, no matter if it's row or column, is going to determine the dimensions of the 2D matrix. In this case, the biggest requirement is 4, so we are going to need a 4x4 matrix to store our shape, and allow all of its rotations. If we apply this logic to every single Tetromino, we end up with this sheet that shows the matrices in all of their rotations. You can see that it respects the rule we have deduced from our observations. We can use it as a base to guide ourselves when representing the shapes in a matrix. You can download a copy of this rotation sheet from the description. Before we continue, I would like to note that I have updated my version of Raylib. I am now using the latest version available, which is 4.0. If you have installed Raylib recently, chances are you already have the latest version. If you don't, I have made a small video that shows you how to update a library using VC package. Link in the description. By the way, if you update Raylib in the middle of the project, you may get some weird IntelliSense errors. In case that happens, all you have to do is open the project in the File Explorer, close Visual Studio, then go to the main folder, and delete this .vs file. Then you can just relaunch the project using the .sln file. And that should fix the IntelliSense errors. Now, let's start by removing all of these red cells from our board. If you remember, we were initializing them inside of game.cpp, inside of this loop, so all I have to do is remove it. But now you can see that our board is still drawing white cells, so clearly there's a problem. So let's check the draw function of our board. If there's a problem, it's probably there. So here, inside of the draw function, we are iterating over every cell in our board and drawing it, and that's where the problem is actually. If you remember the way we declared a cell, we gave it a color and a boolean to tell us whether or not it exists. But currently we're not checking if it exists before drawing. So inside of our cell, let's make a function that tells us whether or not it exists. So it's going to be const and it should return B exists. Oh, and these should be Boolean. And now inside of our board, let's make a bool function that checks if a cell exists. It takes in a vector 2 for the position of the cell, and it's constant. In the implementation, we just access our cell the way we are used to. So we go cells position.y times width plus position.getX. And here we just go exists. And now in our draw function, before we draw a cell, all we have to do is check whether or not it exists. So we can go if cell exists. We give it the position, which is ix, iy, and that's it. Now if we run again, our board is empty, just like it should be. So, how are we going to create our Tetrominoes? If you think about it, they all have similar functionalities. They can all rotate clockwise or counterclockwise. They can move left and right. They all have to keep track of their position in the board, and so on. We can clearly see a lot of shared properties. This situation is a very good candidate for inheritance. It would be best to have one class called Tetromino that implements what the Tetromino can do, such as rotate and so on, and then have all of the different Tetrominos inherit from that class. So let's do that. Let's create a Tetromino class. A Tetromino is going to need to keep track of its position on the board, so a vec2 of int board position. Of course, we need to include vec2. A Tetromino also has a color that we need to remember. For this one, we'll need to include Raylib CPP. Obviously, we will also need to keep a reference to some kind of shape that will determine which Tetromino we have. But how big are we supposed to make the array? After all, we don't know which Tetromino this is, and as we can see in our rotation sheet, Tetrominos have different shape requirements. So clearly, we can't just declare an array of, let's say, 9, because it might be too big or too small depending on the shape. So we'll think about this in a moment. So let's create our first Tetromino using inheritance. We'll go class, straight, and it's going to inherit from Tetromino. The reason why I wrote public here is because I want whatever we wrote in the public section of Tetromino to stay public after being inherited. For example, if I make an int in here, and then straight inherits from Tetromino, it would be as if I made this, which pretty much means that straight contains an integer that is accessible to the public. But if this were private, then whatever is public in Tetromino after being inherited will become private. In other words, x would become private int x. So that was just a quick explanation of different ways to inherit. The advantage of dividing every Tetromino into its own class is that the information of every Tetromino is contained within itself. So the straight class is probably the best place to store how a straight shape is supposed to look like. Static constexpr, an array of booleans, and we'll call it shape. A straight shape is supposed to look like 0, 0, 0, 0, 1, 1, 1, 1, and zeros everywhere else. As you can guess, each cell is represented by a 1. Some of you may ask, why didn't we use a std vector to store this array? Well, think about it. The shape is never going to change. A straight is always going to look like this. And we already know the content of the array. So we have no use for a dynamic array like std vector, which can shrink and grow whenever it's needed. And since this array is never going to change, we make it constexpr, and we make it static so that there's only one copy of it in the whole program. Static will make sure that every single straight object is going to share the same variable. Well, in this case, the same constant. This shape will only exist once throughout our whole program, and it's never going to change. And that's what we desire. Let's do the same for the color. Static constexpr color, color, and we'll give it sky blue. And finally, let's store the dimension of the shape. Static constexpr int dimension. In this case, it's equal to 4. Now let's do the same thing for every single one of our shapes. We'll do that for the square. A square shape is supposed to look like 1, 1, and 1, 1. Obviously, the dimension is 2, and we'll give it a color of yellow. Now for the T shape, 0, 1, 0, 1, 1, 1, and 0, 0, 0. Dimension is 3, and the color is magenta. J shape, 1, 0, 0, 1, 1, 1, 0, 0, 0. Dimension is 3, color is dark blue. The L shape, 0, 0, 1, 1, 1, 1, and zeros. Dimension is still 3, and the color is orange. We have skew S, 0, 1, 1, 1, 1, 0, and zeros. Dimension is 3, color is green. And finally, for skew Z, it's 1, 1, 0, 0, 1, 1, and zeros. Dimension is 3, color is red. Okay, now that we have each information neatly encapsulated in its class, when we create one of these shapes, we need a way of sending all of this information to the Tetromino class. The best way of doing that would be to use a constructor. So here we'll make Tetromino constructor. It needs to take the dimension, the color, and the shape. Question is, how are we going to take the shape? Remember, every shape has its own dimension. We can't just take a Boolean shape of, let's say, 9, because that would only work for shapes with dimensions of 3, because the arrays have a length of 9. What about the ones who have a length of 4 or 16? So obviously, we can't use this. It looks like we are going to have to resort to the old pointers. So we'll go constant Boolean pointer. Some of you may hate to see this, and you would be partially right. Pointers to arrays are not as safe to use as state vectors, for example. So these could eventually bring problems. But don't worry, we will see how to deal with them and even prevent them. So we will also need to take the dimension and the color. So let's create a tetrominoes.cpp file, implement the constructor. Let's create the variables to hold our shape and dimensions. So inside of our Tetromino class, we're going to need a constant bool pointer for the shape and a constant integer for the dimension. So in the constructor, the shape is going to take the shape, dimension takes dimension, and color takes color. Now that we know how to store our shape, let's remove this comment. But we still haven't initialized the Tetromino's board position. Preferably, when we create the Tetromino, we would like it to start at the top center of the board. So in this case, we'll go board position, and for the X, we want it to be the center of the board. So for that, we need to access the board. So in the constructor, let's add a board reference, board, a constant one, because we don't want to modify the board. Let's include board, add it in the CPP file too. And here we go board dot, and we have no way of getting the width and height. So let's go inside of board. Let's add a function that returns an integer, and it's get width, and it's going to be constant because it's just a getter. Let's do the same for the height. When we implement them, they look like this. And now we can go board.getWidth, and we'll divide it by 2 to get the center. And we also need to remove from it half of the width of the Tetromino, otherwise it won't be centered. So we go dimension divided by 2. So that's it for the x, and for the y we'll just put it at the beginning, 0. Let's also create a const board reference to store the reference of the board we receive. We will probably use it later. So let's not forget to initialize it here with board, because it's the role of the Tetromino to be aware of what is happening in the board. Great, so now our Tetromino class is able to receive all of this information. Now all that's left is for each class to pass in its information. So for the straight, we're going to make it public and create its constructor. Let's implement it in the header file because it's going to be a small one. So all we need to do is to call the constructor of Tetromino. To do that, we can just use the list we usually use to initialize our variables. So we go column and Tetromino, and here we can give it whatever we need. So we'll give it the shape, the dimension, the color, and we need a board reference, which this class is going to need to receive. So we'll make it receive a constant board reference board, and then pass it in to Tetromino. It doesn't need to store the board itself because Tetromino is going to do it. But remember when I said that raw pointers are not as safe as stit vector? Well, let's say that instead of passing 4, I end up passing 5. There's clearly an issue here because our shape is a 4x4 shape, and if we mistakenly pass in 5, we will end up trying to read outside of this shape, which will very probably make our program crash. This is such an easy mistake to make and it's hard to detect. So how do we deal with this problem? Well, we have been using assertions all this time to make sure that we don't make a dumb mistake. This time around, we are going to use the brother of assertions, static assertions. So let's go ahead and include assert, and inside of the body of the constructor, we are going to make a static assertion. And the difference between an assertion and a static assertion is that a static assertion is going to be checked at compile time, which means that as soon as we hit the compile button, all of the static assertions are going to get checked. And if one of them fails, the compilation will stop and it's going to point at wherever the problem is. This is very useful because our shape and our dimension are known at compile time. We can check whether or not they make sense. So all we have to do is check if the length of this shape vector is equal to the squared of the dimension. So to get the number of booleans inside of our shape, we can go size of shape, and this is going to return the size of the shape in memory, which means that it's going to return how many bytes our shape is taking. All we have to do is divide it by the number of bytes each boolean takes. So we go divided by size of boolean. So this is going to give us the number of booleans inside of our array, and we have to make sure that it equals dimension times dimension. As you can see, the compiler is already complaining. It's telling us that the static assertion has failed. Now if we fix our dimension, put it back to 4, you can see that the compiler is happy. And of course I forgot a semicolon at the end. So as you can see, we managed to make the compiler work for us. As soon as we make a mistake that is presumably hard to spot, the compiler will spot it for us instantly. And obviously, if I try to compile while it's failing, it's going to refuse compiling, and will point me right to the error. Pretty cool. Even when using raw pointers, there are many ways of making sure they are safe to use. Now all that's left to do is to use the same logic for the other ones. Every other constructor is going to look exactly the same. And so here's the final result. It's pretty much all the same. But I want you to understand that using a stit vector instead of a C array is a totally viable option. It's just that using a C array will allow us to directly tap into the static memory of our program. You see, the memory of our program is divided into 4 main parts. The code instructions we write are stored in the text part. The normal variables we declare are stored in the stack. However, this C array will be stored in the static part of memory. Static variables are not always global. In this case, it's private, only accessible to this class, but they can be global if needed. A static variable will stay alive throughout the lifetime of the program. This is something we desire in this case. And finally, we have the heap, which is used to create dynamic memory like state vectors, which can change their size at runtime. So, when we launch our program, the code part will be loaded. The static parts too, which contains our shapes. In case we use a state vector, we are going to copy the static memory into the heap, because that's where state vectors keep their memory. They can't use stuff that's in the static part of memory, so they have to copy them over to the heap. However, when we use a C array, this array is directly pointing to the static part of memory. We can directly read from it. We don't need to make useless copies, so we will not be using this. Using C arrays and raw pointers is a little bit more work. But again, we want our shapes to be an absolute reference throughout the whole lifetime of the program. Whenever we need to know what our shape looks like, we can access this unchanging part of memory. We are also able to deal with the problems these methods may cause in an elegant way. Our Tetrominoes should now be ready for use. But thanks to the way we have implemented our Tetrominoes, all we need to do is implement a draw function inside of the Tetromino class, and that will take care of drawing any Tetromino no matter its type. Now we make a draw function, void draw constant, for int y equals 0, y is smaller than dimension, plus plus y, and for int x equals 0, x is smaller than dimension, plus plus x. So for each cell in our shape, we need to check whether or not it's 1 or 0 to know if we should draw or not. So we get our cell by going shape at y times dimension plus x, which is the formula we've been using to access our one-dimensional arrays as 2D arrays this whole time. But we'll talk more about this very soon. So we check if our cell is true. It's true if it's different from 0. Then all we have to do is go board.drawCell, and we need to give it a position. The Tetromino tracks its own position. We can just go board position, and we just need to add a vector 2 x, y, because we have to take into consideration which cell we are checking inside of our shape. And that should be pretty much it. Now let's test our Tetrominoes. Inside of game.h, let's include Tetrominoes. And here let's declare one. For example, we'll take a j. And if we check the CPP file, the compiler is complaining here because j has a constructor that requires something. So we have to give it here. We go Tetromino, and it requires a board. So we'll just give it our current board. Now let's go ahead and draw it. So we go Tetromino.draw. And remember, Tetromino is a J class, which does not have a draw function. It got it from its parent, which is Tetromino. Okay, now let's try to save and run. And as you can see, it's working. The only issue is that it's not drawing using the Tetromino's color. It's still drawing in white. And that makes sense because the draw function is calling board.drawCell. And drawCell uses the color it finds on the board at this location. And by default, the whole board is white. So, to be able to draw using the Tetromino's color, I think that we are going to need another version of drawCell. One that ignores the color it finds on the board and uses another one instead. Inside of board.h, we are going to overload our drawCell function. So this time around, it's going to take the position and a color. The implementation is going to be exactly the same as the first one, except that we don't need to get the color from the board. Instead, we are going to use the color we receive as an argument, just like this. But you can easily see that we are kind of copying code here. We can actually easily make this draw function work using this one. All we have to do is make it get the color from the board. We don't need the assertion either, and then make it call this draw function. We give it the position and the color we found. Let's actually change this to color, just like this. Now we don't have duplicate code anymore. Great, so now inside of our Tetromino, we don't call draw cell like this, we add a color to it, which is the current color of the Tetromino. And now if we run again, we are drawing using the Tetromino's color. Perfect. And that's pretty much it for the first part of this video. The second part is available here, or in the description. In any case, take care of yourselves and see you soon.